Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to discuss about the module Defect Chemistry, that is part 4 from the paper Ceramic. So students, let us see what we are going to learn in this module. So we will be learning about the defect equilibria in non-stoichiometric oxides, and we will be determining the defect concentration as a function of partial pressure of oxygen. Then we will be drawing the Brouwer's diagram according to the defect concentration. So students, before moving further, let us clear some basic idea. So the crystalline solid exists a periodic crystal structure, and the position of atoms or molecules occur on repeating fixed distances determined by the unit cell parameter. However, the arrangement of atoms or molecules in most crystalline material is not perfect. So the regular pattern are interrupted by the crystallographic defects. So the point defects are the defects that occur only at around a single lattice point. They are only extended in space in any dimension. So the strict limits for how small a point defect is are generally not defined explicitly. However, these defects typically involve at most a few extra or missing atoms. Larger defects in an order structures are usually considered dislocation loops. So, for historical reasons, many point defects, especially in ionic crystals, are called centers. For example, a vacancy in many ionic solids are called luminescence center, or we call as color center or F center. So these dislocations permit the ionic transport through the crystals, leading to electrochemical reactions. So these are frequently specified using Kroger-Wink notations, and some of the defects are vacancy defects. So the vacancy defects are the lattice sites which would be accompanied in a perfect crystal but are vacant. So if a neighboring atom moves to occupy the vacant site, the vacancy moves in opposite direction to the site which used to be occupied by the moving atom. So the stability of the surrounding crystal structure guarantees that the neighboring atoms will not simply collapse around the vacancy. So in some materials, the neighboring atom actually move away from a vacancy because they experience attraction from atoms in the surrounding. So a vacancy, or we call a pair of vacancies in an ionic solids, is sometimes called Schottky defects, and another defect which come is interstitial defects. So interstitial defects are atoms that occupy a site in the crystal structure at which there is usually not an atom. They are generally high energy configurations, and small atoms in such big large crystals can occupy interstices without high energy, and such as hydrogen in palladium. So the schematic illustrations of some simple point defects will be mentioned in this module, and this module will also be focusing on the Frenkel defect. And the Frenkel defect arises when a nearby pair of vacancies or interstitials come into picture. So let's see how we are understanding the defects, that is Frenkel and Schottky defect. So first we are discussing about the defect structures involving oxygen vacancies and interstitials. So depending upon the partial pressure of oxygen, an oxide may be oxygen deficient or metal excess, or it can be metal deficient. We can call it as oxygen excess. So let us consider the following conditions in an oxide, that is MO. So the first is low partial pressure of oxygen, that is oxygen vacancies dominate. The second is high PO2, that is oxygen interstitials dominate. The third is an intermediate PO2, that is oxide is stoichiometric. Now, assuming that both oxygen vacancies and oxygen interstitials are doubly changed or fully ionized, the defect reaction can then be written as, for low partial pressure, the defect reaction is OO gives half of O2 plus concentration of VO double dot plus 2 electrons. Corresponding reaction constant, assuming that concentration of MM and OO are equal to 1, then the reaction constant is K of VO double dot is equal to partial oxygen pressure to power 1 by 2 times the concentration of VO double dot times Ne square. However, at high partial pressure of oxygen, the defect reaction becomes half of O2 gives OI double prime plus 2 holes. Hence, the reaction constant becomes KOI double prime gives concentration of OI double prime times NH square by PO2 to power 1 by 2. At intermediate partial pressures of oxygen, that is PO2, the stoichiometric defects are likely to prevail, that is, either through intrinsic ionization or through anti-Frenkel defects. So the first is intrinsic ionization of electrons and holes. So in this case, 0 gives electron plus hole, and the corresponding reaction constant is Ki is equal to Ne times NH. Similarly, the formation of oxygen Frenkel defects, that is anti-Frenkel defects, leads to OO gives OI double prime plus VO double dot, with the reaction constant as Kf here is used for the Frenkel. So Kf is equal to concentration of OI double prime times VO double dot. So from the above relations, we can write Kf times Ki square is equal to KVO double dot times KOI double prime. So here Kf is the reaction constant due to Frenkel defects and Ki is due to intrinsic ionization. Now comes limiting condition. So the first limiting condition is low partial pressure of oxygen. So this results in oxygen deficit, or we can call it as metal excess. So the second limiting condition which we will be discussing is intermediate partial pressure oxygens, that is stoichiometric composition. The next limiting condition is high partial pressure of oxygen, that is oxygen excess or metal deficiency. So the first case is low partial pressure of oxygen, that is oxygen deficient. At large oxygen deficient, we can assume that VO double dot concentration is equal to half of Ne, which is much greater than the concentration of OI double prime. Therefore, the previous equation becomes the concentration of VO double dot is equal to half of Ne, which comes to be the K of VO double dot by 4 to power 1 by 3 times the partial oxygen, that is PO2, to power minus 1 by 6. Substituting the value of Kf, we get the concentration of OI double prime, which is Kf upon VO double dot concentration, which is equal to Kf times KVO double dot by 4 to power minus 1 by 3 times PO2 to power 1 by 6. So the equation for the concentration of holes become NH is equal to Ki by Ne, which in turn can be written as Ki times 2K of VO double dot to power minus 1 by 3 times PO2 to power 1 by 6. So combining all the above equations, we get the condition that PO2 is very much less than KVO double dot square divided by 16 Kf cube. Now the second case is excess of oxygen, that is high partial pressure of oxygen. So at large oxygen excess, we can assume that the concentration of OI double prime is equal to half of NH, which is much greater than the concentration of VO double dot. So in such situations, we get that the concentration of OI double prime is equal to NH by 2, which is equal to KOI double prime by 4 to power 1 by 3 PO2 to power 1 by 6. So the equation for VO double dot, that is the concentration, becomes Kf by OI double prime, which in turn equal to Kf times KOI double prime divided by 4 to power minus 1 by 3 into PO2 to power minus 1 by 6. Now combining the equations, we get Ne is equal to Ki into twice of KOI double prime to power minus 1 by 3 PO2 to power minus 1 by 6. So combining all the above equations, we get the condition that PO2 should be greater than 16 Kf cube to power KOI double prime square. So the third case is stoichiometric conditions, that is intermediate PO2, that is intermediate partial pressure of oxygens. So the first case is intrinsic ionization dominations, that is where intrinsic ionization is dominating. So the defect reaction is O gives one electron and a hole, that is corresponding reaction constant can be expressed as Ki, which is equal to Ne times NH, or Ne is equal to NH, which is equal to Ki to power 1 by 2. So Ki to power 1 by 2 comes out to be very much greater than the concentration of VO double dot and OI double prime. So here both Ne and NH are independent of partial pressure of oxygens, while the point defect concentrations are given as the concentration of VO double dot is equal to KVO double dot divided by Ki times PO2 to power minus 1 by 2, and similarly the concentration of OI double prime is equal to KOI double prime divided by Ki times PO2 to power 1 by 2. Now the second case under stoichiometric condition for the intermediate partial pressure is internal disorder and anti-Frankel defects which dominates. So here the reaction is the concentration of OI double prime is equal to VO double dot, which is equal to Kf to power 1 by 2, which founds to be very much greater than Ne and NH. So now since the concentration of OI and VO double dot are independent of partial pressure of oxygen, so using the previous equations for Ne and NH, we get Ne is equal to KVO double dot to power 1 by 2 divided by Kf to power 1 by 4 times PO2 to power minus 1 by 4. Similarly, NH is equal to KOI double prime to power 1 by 2 by Kf to power 1 by 4 times PO2 to power 1 by 4. So the above equations provide the limiting conditions for the oxygen partial pressures separating into three regions, which we will be discussing in the next slide by the schematic. So as we have discussed in the previous slide that the limiting conditions of oxygen partial pressure separating three regimes of oxygen pressure with various concentrations of defect as a function of partial oxygen pressure can be obtained, and this result in Brouwer's diagram. So let us discuss this diagram for the first defect, that is Frenkel defect dominating at stoichiometric composition. So students, you can see on the left hand side of the slide, the diagram is obtained when Frenkel defects dominates, that is internal disorder of the material dominates in the intermediate pressure range. The best way to draw the diagram is to first draw the central region, that is making V0 is equal to OI, and then extend the lines of VO and OI into lower and higher pressure regions with appropriate slopes depending upon the oxide stoichiometry. Then draw the electron and hole concentrations, that is N and P, in the low and high pressure regions respectively, since their relationship to V0 and OI is straightforward. Then you can extend these in the intermediate region and low or high partial pressure of oxygen region depending according to the slopes obtained from the analysis. So this process yields the diagram which is shown on the left hand side. Now let us discuss the Brouwer's diagram for the intrinsic ionization dominating at stoichiometric composition. So using the procedure similar to that explained in the previous slide, except that in the central region now N is equal to P, as intrinsic ionization dominates at the stoichiometric composition. So we obtained the figure which is shown on the left hand side of the slides. So there are subtle differences as we can observe by comparing the two figures which we observe from Frenkel and for ionization. So students, let us discuss a simple general procedure for constructing a Brouwer's diagram. So there are the simple steps which I will be discussing right now. So the first step is first determine how many defects are relevant. Then write independent defect reaction for each defect and K value. Then write N1 equations which will be obtained for N defects, and then define the regions of partial pressure of oxygens. So observe which defect concentration decreases or increases with the change in partial pressure of oxygen. So students, let us summarize what we have learned in this module. So students, we have discussed and learned that the determination of the concentration of various defects from the defect reaction in different regimes of partial pressure of oxygen, which is possible by knowing the limiting condition which will lead to the boundaries between various regions. Moreover, we have read that from these concentrations one can draw Brouwer's diagram which depicts the variation of concentration of various defects and in turn electrical conductivity as a function of partial pressure of oxygen. Thank you.